Good day, everyone. I am Maria Carmen Concepcion, the Tiquis from BS Geological Engineering 3201, and I'll be presenting under the topic of volcano monitoring and early warning. The title of this study I'll be presenting is Deciphering the Whisper of Volcanoes, Monitoring Velocity Changes at Kamchatka's Klyuchevskoy Group with Fluctuating Noise Fields. This work was authored by Peter Makus, Alexander Yates, Christoph Sens-Schonfelder, and Frederick Tilmann. Let us explore how subtle changes in seismic velocity can reveal vital information about volcanic processes and how these researchers applied innovative techniques to one of the most active volcanic regions in the world. Why study it? Volcanoes rarely erupt without warning, but catching those signs is the real challenge. Traditional monitoring tools like satellites, tiltmeters, and seismic networks often pick up on the formation or earthquakes before eruptions, but these signals vary widely between volcanoes. And that's why researchers are turning to new methods like passive image interferometry, which uses the Earth's constant background noise to detect small changes in the rock properties. In this study, the authors explore how to apply this technique in one of the world's noisiest and most active regions in the world, Kamchatka's Klyuchevskoy group. So, before we dive into the methods and findings of this study, it is important to understand the unique setting of the Klyuchevskoy Volcanic Group, or KVG, located at the central Kamchatka Depression on Russia's far east peninsula. This region sits atop of a subduction zone where the Pacific Plate dives beneath Okhotsk microplate, in which this tectonic setting fuels both intense volcanic activity and frequent large earthquakes, such as the magnitude 7.2 Zupanov earthquake that occurred during the study period. Next is we will discuss the study area. This figure shows the geographical context of the study, in which in panel A we see the wider Kamchatka Peninsula with seismic stations marked, squares for permanent stations, and triangles for the temporary ones deployed during the KISS experiment. The sign marker highlights the station X9IR1, which plays a key role in the analysis. You'll also notice a magenta star to the south, in which marks the epicenter of the magnitude 7.2 Zupanov earthquake that occurred in January 2016 and had a noticeable impact on seismic velocity measurements in this study. Panel B then zooms in the central study area, outlined by the red dashed box. This close-up shows the three active volcanoes that the paper focuses on, the Bezmiany, Klyuchevskoy, and Sheveluk. Next, move on to the data processing, in which this gives us an overview on how the seismic data was processed to estimate changes in the subsurface velocity, in which the study used one full year of continuous seismic data collected from 101 stations deployed across the Klyuchevskoy volcanic group. 77 of these stations were part of the temporary KISS experiment, and 24 were permanent stations operated by the Kamchatka branch of the Russian Academy of Sciences, in which in this study they retrieved stable subsurface velocity estimates for four 1-octave wide frequency bands between zero point 0.5 and 8 Hz during the shorter time segments by exploiting uniform noise fields that are temporarily stable and thereby obtain high resolution DVV time series that reveal fast acting, shallow, medium changes and their accurate timing. The processing started with the standard pre-processing steps in which the data was downsampled into 25 Hz, detrended, tapered, and bandpass filtered in octave-wide frequency bands. To suppress amplitude effects and focus on the waveform shape, the data was spectrally whitened and normalized using one-bit filtering, in which preserves the sign but removes the amplitude information. The clean data was then split into 1-hour windows and three types of correlation functions: cross relation cross correlations, self correlations, and autocorrelations. And to achieve these data correlations, the authors use trace stretching techniques from Sens-Schonfelder and colleagues, where we take small time windows of seismic data, stack them to reduce noise, and then compare each to a reference signal, in which we stretch the signal slightly back and forth to find the best match. And the amount we have to stretch tells us how much the wave speed has changed. This gives us a time series of the DVV, or relative velocity change, and also tells us how much or how stable each measurement is. And it is fairly simple but a powerful way to track how waves travel through Earth over time. Next is the passive image interferometry, in which is a technique in seismology used to monitor changes in the Earth's subsurface by analyzing naturally occurring seismic noise. The PII uses background vibrations of the Earth, like ocean waves, wind, human activity, and are recorded by seismic stations to measure how fast seismic waves travel through the ground. And by comparing these wave speeds over time, the scientists can detect small changes in the underground structures, such as those caused by magma movement, earthquakes, or weather effects. Next is the problems with PII, in which we have the volcanic tremors dominate the noise. Next is standard pre-processing techniques are not enough. Next is abrupt fluctuations in DVV estimates. Next is the misleading high correlation during tremors. And in short, PII struggles when the background noise is messy and is constantly changing like near active volcanoes because it depends on consistent, stable noise to detect the real underground changes. With that, the researcher's solution with PII is the time-segmented passive image interferometry, or TSPII, in which um, improves stability because it reduces the impact of non-stationary noise like volcanic tremors. Next is higher temporal resolution because it allows shorter time segments in which could be analyzed accurately. Next is noise-aware analysis, in which by segmenting based on noise similarity, it avoids mixing incompatible data. Next is it is flexible across stations. And lastly, it combines trends of machine learning and classical methods, where machine learning is used to organize data, but velocity changes are still needed to be interpreted using interferometry. Next is for its results. The authors used 1 year of seismic data from station X9RR1 to perform hierarchical clustering on self-correlations. This process groups data based on how similar the background seismic noise is over time, where A dendrogram shows how similar or different the clusters are, meaning tall branches equals more different. Next is the timeline, which shows when each cluster appears throughout the year, revealing how noise conditions change over time. And lastly, the average correlation functions, which shows the typical signal shape for each cluster, proving that they are physically different. Next is the authors use the sequencer algorithm to analyze the similarity of DVV responses from different stations based on their similarity matrices or how their wave speeds change over time, in which the sequencer output stations with similar DVV behavior are placed close together in the sequence, shown as similarly colored and sized circles. Clear subgroups form, like stations on the sedimentary basin, the Klyuchevskoy volcanic group, and the eastern ridge. Next is for B station grouping map based on these results and visual inspection, the stations are grouped into 5 regional subgroups for further analysis. This grouping is critical for spatial stacking, where the DVV measurements from similar stations are combined to reduce noise. Next is this figure shows how seismic velocity changes over time for the central Kamchatka Depression station group using high frequency data from 4 to 8 hertz. In this figure, colored circles are each point where DVV measurement every 2 hours from 4-hour time windows. Next is the color scale, in which measurement quality based on cumulative correlation coefficient. The red dashed lines are times of nearby earthquakes ranging from greater than magnitude 4.8. Black dashed lines are a simple model predicting how DVV based on weather data, rain, and snow. The bottom panel plots the precipitation, blue, and snow depth, gray, average for the region. And next is the lava discharge rates for the two volcanoes, red for Klyuchevskoy and blue for Bezmiani, in which are shown at the bottom for volcanic context, in which this clearly shows the DVV drops after heavy rainfall or snow, then gradually recovers. Imagine the ground as a sponge. When it rains, the sponge gets heavier and softer, slowing down how fast waves move through it. This figure shows that the sponge effect in action, and also proves that TSPII can detect it. So, for our conclusions, the passive image interferometry or PII and pre-processing techniques that were previously used were insufficient for evaluating high frequency and high resolution KVG data. And this is addressed in the paper by introducing an innovative approach that enables efficient PII even in the presence of persistent noise fluctuations, in which is the time segmented passive image interferometry in order to provide more precise and temporally refined velocity change estimates through the spatial averaging. TSPII employs hierarchical clustering to pinpoint time periods with stable noise circumstances. And this approach works best in places where steady noise sources last for long periods, like volcanoes, but it is less appropriate for places where noise fluctuates quickly and irregularly. Next is the seismic velocity change observations, in which are presented in the five Kamchatka regions following the use of the TSPII method and spatial averaging. Strong environmental influences, particularly precipitation and snow depth on shallow subsurface velocity, were revealed by how frequency data in which are shown to be more sensitive and less noisy than lower frequency data, while snow accumulation results in velocity increases and precipitation causes short-term velocity decreases because it increases pore pressure. And these results demonstrate how well the SPII works for non-invasive economical groundwater dynamics and VADOS zone monitoring. In addition to the environmental influences, the study finds significant velocity decreases brought on by tectonic activity, including the magnitude 7.2 Zupanov earthquake, in which it's interesting to note that based on the shaking intensity, volcanic locations like KVG and Shivilak displayed stronger responses than anticipated, in which this is probably because volcanic rock has a high fluid content and nonlinear characteristics. Furthermore, the Bezimiani volcano shortly after the Zupanov tremor, which marked the beginning of the 2016-2017 eruption cycle, in which a significant velocity increase and decorrelation in the noise correlation functions were noted, in which this is thought to be a reaction to inflation in shallow reservoirs. But all things considered, the study shows that PII, TSPII, are an effective tool for monitoring volcanoes in near real time, providing a higher temporal resolution than those satellite based techniques. And that's all. Thank you for taking the time to listen to this presentation. Your attention means a great deal, especially in a field where careful observation and listening, both to people and the earth, are essentials. Just as with people, volcanoes speak long before they roar. Listening carefully can reveal the early signs that helps us understand, prepare, and respond. Again, thank you.